memorable. I'm really happy to be here and glad that they're doing well too. The other memory that I had was being part of NCC for 3 years. I remember the days where you get up early in the morning, 5 a.m., dress up in the NCC uniform, walk up for the parades, the rifle training. All that is so memorable. And I'm telling you for a real fact is that because it helped me shape my disciplined and organized life. And that helped me go do better in the outside world where you adapt to new environments. The other memory that I had over here was being part of IAST. It helped me pursue internship in China, which let me learn new cultures, new language, different people who speak different languages. All that was so exciting and interesting to learn about. The other thing that I learned in Karunya was music. Now you all know Karunya is famous for music and many other talents. I picked up guitar. I used to play for worship. And currently in the US, I play at different bars and different restaurants for a gig. And I remember in Karunya, I used to also be part of the Mega Play. In 2014, I was the stage director. And in addition to that, I used to perform cardistry magic for different organizations in Karunya, being part of different communities and hosting the events as I was the master of ceremonies. All that shaped into a person that I am today. And I'm really happy and really glad. Karunya had such an amazing weather and it not too cold, not too hot. It was pretty, I would say the perfect amount, you know. In the end, all I want to say is thank you, Karunya. Thank you, friends. Thank you, professors. Thank you, everybody who helped me shape my career, helped me become what I am today. And thank you, God. Thank you so much.
Lucia? Can we play the other video also?
Yeah, sir.
The Department of Electronics and Communication Engineering, established in the year 1986, offers 2 undergraduate programs and 2 postgraduate programs, one on communication systems and the other on VLSI, in collaboration with Messrs. Test and Verification Solutions, Chennai. The department is also home to several research scholars pursuing their doctoral degree. Further, students from various countries across the globe intern for a semester in the department through the IAESTE program. Students are also encouraged to take up industry internships, resulting in a number of core and product-based company placements. The department also houses state-of-the-art labs with the objective of developing innovative ideas and achieving excellence in research and training industry-ready professionals. The lab contains industry-standard VLSI EDA tools such as TCAD and Cadence 11 Lab, which is a single machine that can perform all the required steps to create an antenna or a prototype PCB board. A Center for Research in Semiconductor Devices, used extensively for fabrication and modeling of semiconductor devices, has also been established in the department. Collaborative research projects are carried out with the Department of Space, ISRO, and the Ministry of Defense, DRDO, in this center. The IoT Center is equipped with the latest chips provided by IoT giants like Texas Innovation and Intel Intelligent Labs to develop systems for solving societal problems. In placement training, the focus has been on analog, digital, and radio frequency circuits, communication and signal processing, VLSI and embedded systems, networking, computer vision and image processing, control systems, robotics, and nanotechnology. Emphasis on industry internship has resulted in core and product-based company placements. Few of the top recruiting companies of the year are Tata Elxsi, Accenture, Zoho, Wipro, Infosys, CGI, Indus TechSite, Test and Verification Solutions, Jasmine Infotech, Leica Wireless Communications, etc.
Jenkins, shall we start? It's 11.
Yeah, yes, sir.
Welcome participants to the third day of this 5-day FDP. And I could see many of you joining along with us in the initial time of the Zoom meeting. So it shows your thirst and it is very encouraging for us. And we are here to cater all your technical needs. So this third day so far will give us a small summary of what we have seen last day. We saw about convolution neural networks, which is one of the predominantly used deep learning method. So to be frank, deep feed-forward neural network was the first one. CNN is not the first one. DFNN is the first one. But the problem with most of the methods are they are position sensitive to the data. That means if your region of interest, or if the digit 8, or if a car, if it is seen in the middle of the image, then all the methods will solve that properly. But if it is in that one corner of the image or bottom or somewhere in the side, your system fails. So that is the main reason why convolutional neural network came into existence. Convolution is the process which determines or which provides the system to detect irrespective of the position of your data. That's why we say CNN always gives more accuracy in comparison with the other data. And more importantly, you must understand that CNN is a shape-based method. It is going to detect your portion in the image using the features, low-level features and high-level features. So you must be very careful when you are choosing a deep learning method, whether it is suitable for you or not. And there were a few questions about the structure. How to define a CNN is not yet revealed. Some people use a combination of a max pooling layer and convolution layer, but the choice is based on the user. And the softmax function, it is mainly used for a multi-level classification application. Normally, we'll go for sigmoid function for backpropagation neural networks. But when you go for a multi-level approach, multi-level classification, if you have output classes more than 2, then research says or literature survey says your softmax works well. Even you can check replacing your sigmoid function in BPN with softmax, how it works. You can have a check. ReLU is the simplest one because deep learning is already suffering from a huge computational complexity, which is one of the research problem for any scholars. But ReLU usage can minimize it to some extent. That's why we go for such type of setup in convolutional neural networks. And application-wise, as Dr. Clement told, last day car detection, or in a broader manner, you can go for surveillance detection. Surveillance applications in military or in traffic or in any religious festivals. You can go for detecting the anomaly behaviors, something like that. Even we are doing interesting work on detecting the face mask. Nowadays, if as coronavirus is getting much intense, people are asked to wear mask wherever they go in the public, as per the recommendation of WHO also. Now they say it is airborne. So if there is anyone who is violating the law or the rule of not wearing the mask, we can easily detect. such interesting, the database is available in Google, in the net. So such interesting works can be done with the help of object detection and CNN. So that's what I want to say. Now we go into the today's agenda. I welcome Dr. Varun Gopi from NIT Trichy. I have lots of collaborations with him. We have some collaborative publications with him. I know the Varun's efficiency. Is a very hard worker and deeply interested towards deep learning, with specifically with medical image processing. He will give, I'm sure he is going to give all the contents in a different dimension. Now over to Dr. Jenkins to give a brief introduction about Dr. Varun.
Thank you, Professor Jude. We'll start. A candle loses nothing by lighting another candle. We hope we are getting brighter and smarter than yesterday, glowing together. Good morning and welcome back to today's session to all our bright minds. I would like to remind few instructions before I introduce the speaker. Keep your microphones on mute and disable your video during the speaker's presentation. Those who would like to interact with our speaker can post your questions after the end of his presentation. Please keep your questions relevant and precise. The participants can post your questions in the Zoom chat box, or you can come live over with your question. The attendance sheet will be posted at the end after the question and answer session starts. Let me introduce today's speaker, Dr. Varun P. Gopi. Dr. Varun P. Gopi, who will be sharing his expertise on deep learning for image processing applications today, holds a PhD in medical image processing from National Institute of Technology, Tiruchirappalli, Tamil Nadu. He is a recipient of Canadian Commonwealth Scholarship Award for 6 months under Graduate Student Exchange Program in the Department of Electrical and Computer Engineering, University of Saskatchewan, Canada. Apart from this, he has received other fellowships like Research Fellowship and Gate Fellowship from MHRD during his academic tenure. At the moment, he is associated with NIT Tiruchirappalli as assistant professor and is guiding around 7 PhD scholars. He is currently managing 3 projects to a worth of rupees 70.98 lakhs, funded by Vandy Technologies Singapore, SERB India, and Airport Authority India. He has authored, co-authored more than 50 articles as books, book chapters, conferences, journal papers. He has been associated with several conferences, workshops, and symposia as chairperson, organizing secretary, and coordinator. He is acting as a reviewer of several reputed journals published by IEEE, IET, Elsevier, IET, and Springer. He has been given several invited talks on topics like compressed sensing, sparse signal processing, mathematical modeling in medical diagnosis, deep learning, and many more. He is also doing an established research and development in collaboration with eminent professors from Canada, UAE, and UK. We would love to hear from you, our young and dynamic speaker, Dr. Varun Gopi. Over to you, Professor.
Thank you. Thank you all for the wonderful introduction. Okay. So today, my session, I would like to talk about the basics of deep learning first, followed by the applications. Is it visible?
Yes, yes, Varun. Yes.
Okay. Fine. Okay. So good morning, all. Today, I would like to start with a brief introduction to deep learning, followed by its application. So, as all of you know, actually, artificial neural networks are the first networks which hello. Okay, ANN are the first networks which we have used, and ANN comprises of many interconnected simple functional units or neurons that act in concert as parallel information processor to solve classification or regression problems. So ANN as of now, one of the most widely used approaches to computational intelligence started as an attempt to mimic adaptive biological nervous system. So it is mimicking the nervous system. So that's why it is known as neural network. So ANNs have been studied for more than 70 years, during which time they have waxed and waned in the attention of researchers, have made a strong resurgence again. Nowadays, we are dealing with deep learning. So as ANN, we can see that from the picture, the first section is input layers, which are interacting with surrounding environment. And the next one is passing this interacted information back and forth between layers with black box for processing by invoking certain design calls and learning rules. So these layers are known as the hidden layers. So n number of layers will be there. So there is an output layer finally. It will relay the processed information out to the surrounding environment. So we have input, hidden and output layers in this ANN. So then there may be a chance of question, how does network learn? So we have to answer that. So neural networks are capable of learning by changing the distribution of weights. It is possible to approximate a function representative of patterns in the input. So by changing the distribution of weights, we can learn the network. So that is the basic idea behind neural networks. So the key idea is to re-stimulate black box using new excitation data until a sufficiently well-structured representation is achieved. So whenever we are getting a well-structured representation, till that moment we have to stimulate the neural network. So each stimulation redistributes the neural weights, hopefully in the right direction. And learning then is the aggregation of variable length of causal chains of neural computations, seeking to approximate a certain pattern recognition task through linear or nonlinear modulation of the activation of neurons across the architecture. So here we are considering the pattern recognition, mainly doing the pattern recognition through linear or nonlinear modulation of the activation of neurons across the entire architecture. So now we move on to deep neural networks. So deep neural network is nothing but it's a stack up of different neural networks. So the term deep in this context is a direct indicator of space complexity of the aggregation of chain across many hidden layers to learn sufficiently detailed representation. As we know, if you go for a small number of layers, it won't learn that much. So deep in the sense, we have a lot more stacks of hidden layers to learn the network. So this deep neural network has grown in the light of its ability to scale with input data and its capacity to generalize across problems with a similar underlying feature distribution. So taxonomy of AI. So in the taxonomy of AI, DL, which uses either deep architecture of learning or hierarchical learning approach, is a class of machine learning. Here we have the taxonomy. AI is the whole one. In that we have machine learning. Then there is a brain-inspired learning. In that brain-inspired learning, we have neural network. We have deep learning. We have SSN, that is spiking neural network. It is another kind of ANN that is very close to the natural neural network. And in addition to the neuronal and synaptic state, this SSN incorporate the concept of time into their operating model. That is the advantage of SSN. So this is the taxonomy of artificial intelligence. So next is feature learning. So a key difference between traditional machine learning and DL is how the feature is extracted. So in traditional ML approaches, we are using handcrafted engineering features, and by applying these, several features extracted through handcraft methods will be given to the classifiers like SVM, MLP, all those classifiers. So there we are handcrafting the features. Say for example, for an image processing case, we are going to detect a cancer. So we are taking first the image, you segment the image, detect the portion where the cancer is there. Then we have to take the feature to check whether it is malignant, affected, or benign, normal. So this is the normal procedure. So here we have to use our own methodology to detect the feature. Additionally, other boosting approaches are often used where several learning algorithms are applied to feature of a single task or data set, and a decision is made according to the multiple outcome from the different algorithms. So say for example, if you're going for a classification purpose, you can use SVM classifier, MLP classifier, random forest, or AdaBoost, any classifier you can use, and you have to you have to verify that which classifier is giving you the maximum accuracy. So there you have different options in classification. So next is deep architecture. So there are numerous deep architectures available in the literature. So comparison of architecture is difficult, as Jude sir told in the initial session, because the comparison of architecture is difficult as different architectures have different advantages based on the application and the characteristics of the data involved. So we can't compare these architectures. So in vision, especially in computer vision, convolutional neural networks, and for sequences and time series modeling, we are using recurrent neural networks. So the deep learning is a fast evolving field, and every year various architectures with various learning algorithms are developed to create human-like efficient machines in different domains of application. So next is deep feed-forward network. This is the first kind of deep network where we have n number of input layers and n number of hidden layers and p number of input units and q number of output units. As you see, you can see there are a lot more hidden layers are there. So that's why it is known as deep feed-forward network. You have more number of hidden layers. So next is the main network, that is the convolutional neural network, CNN. So the CNN having a structure like convolution pooling, flatten, ReLU, then fully connected, and finally the output layer. So we have a special session for convolution layer, how we are going to design. So we will discuss this convolution layer later. And next is the recurrent neural networks. So in recurrent neural networks, generally human thoughts have persistence. So humans don't throw a thing away and start from thinking from its scratch. So the traditional ANNs cannot deal with this type of problem. So the standard neural networks and CNN are incapable due to the following reason. First is these approaches only handle a fixed size vector input, say for example an image or a video frame, and produce fixed size vector as output, say for example probabilities of different classes. And secondly, the models operate with fixed number of computational steps. That means the number of layers in the model. But on the other hand, the RNNs are unique as they allow operation over a sequence of vectors over time. You can see the structure of RNN. So here you can see that the output layer, input layer is there, hidden layers are there, output layers are there. So in a single structure, you can represent using the first figure, or if you unfold the structure, you can see the next figure. Here you can see a loop allows information to be passed from the one step of the network to the next. And a recurrent neural network can thought of a multiple copies of same network, and each network passing a message to the successor. And also, if you look at this picture, you can see that it can receive an input at xt minus time, t minus 1, xt, and xt plus 1. So it can access the information at different times, and also it is passing the information to the next successor. So this is the advantage of recurrent neural network, because it can be used for processing video sequences. So next is generative adversarial network, or GANS. So in GANS offer an alternative approach to maximum likelihood estimation techniques. And GAN is an unsupervised deep learning approach where two neural networks compete against other in a zero-sum game. Here we have two networks. The first one is generator and the second one is the discriminator. So here you have actual samples. Those samples will be given to the discriminator along with a latent random variable based generated image sample is also given. Discriminator will discriminate this original and the duplicate one and give the loss function back to the generator. Based on the loss function or the difference, this generator will generate the image again and it is become more close to the original sample. So this can be used in face detection and face super resolution as an application. And here the zero-sum game means here the discriminator and generator are competing each other. So there is a win-win state. That means both discriminator and generator getting a equal amount of profit. So the generator starts with the Gaussian noise to generate images, and the discriminator determines how good the generated images are. This process continues until the output of the generator become close to the generated one. Next is transfer learning. This is another one of the important topic in deep learning. So this transfer learning make use of the knowledge gained while solving one problem and applying it to a different but related problem. Say for example, the knowledge gained while learning to recognize car can be used to some extent to recognize trucks. So say for example, we are training a network with car images. So it may be sometime used for testing the truck images. So next one is pre-training. So as of now, there are a lot more pre-trained networks are available, developed by Google. So a network is trained with big amount of data, and during the training, the model learns the weights and bias. So the problem with the pre-trained network is that they are having huge number of layers and they are trained on specific data set. Say for example, ImageNet database. Google is mainly training their data structures on ImageNet. So once it is trained on that particular data set, these networks have a particular weight values and bias. And if you are using the same weights in another data set, we can use it as a transfer learning. We can say it is a transfer learning. Second option is we can fine tune. So these weights can be transferred to other networks for testing or retaining a similar new model. So the network can start with the pre-trained weights instead of training from scratch. That means you can use the existing pre-trained network and you can change some of the layers of the network and you can train the new network so that new data set will be trained on the network. So initial weights will be the weights of the pre-trained networks followed by the new layers of the network. So this is another way of implementing transfer learning. So from this picture, we can see initially we are having a source model. So we are training the samples on ImageNet data. After training on ImageNet, you are getting a certain weights and bias. So these weights and bias will be transferred to the next model, target model. And here we are testing using another data set. Say for example, Pascal data set we are testing. So here we are using the same weights and bias of the previously trained network. That's why the transfer of weights taken place here. That's why it is known as transfer learning. Another option is you can use the same weights along with you can add one or more layers to the existing network and you can train your data and again test. This is the concept of transfer learning. So why we are going for deep learning? That is another question. So it's a universal learning approach. So DL approach is sometimes called universal learning because it can be applied to almost any application domain. And second one is it is robust. Deep learning approaches do not require the precisely designed feature. Instead, optimal features are automatically learned for the task at hand. So robustness to natural variations of the input data is achieved. And generalization. So the same DL approach can be used in different applications or with the different data types. Say for example, with the transfer learning, as I mentioned earlier. So in addition, this approach is helpful when do not have sufficient available data. Say for example, if you don't have available data to train, you can use a pre-trained network because it is already trained on a set of data. So you can use the same data structure for testing. So next is scalability. So the DL approach is highly scalable. So Microsoft invented a deep network known as ResNet, and this network contains 1,202 layers and is often implemented at a supercomputing scale. And there is another big initiative at Lawrence Livermore National Laboratory, LLNN, in developing frameworks for networks like this, which can implement thousands of nodes. So in deep learning, a computer model learns to perform classification tasks directly from images, text or sound. Here, there is no human intervention inside the deep learning architecture. The network itself learns. So the deep learning models can achieve state-of-the-art accuracy, sometimes exceeding the human level performance. So that is the advantage of deep learning. That's why we are going for deep learning. Next is some of the applications. So the deep learning architectures such as deep neural networks, deep belief neural networks, recurrent neural networks, and convolutional neural networks have been applied to fields including computer vision, speech recognition, natural language processing, audio recognition, social networking, machine translation. So these are some of the examples of applications of deep learning: image recognition, restoration, drug discovery and toxicology, recommendation systems, bioinformatics for security systems, medical image analysis, forecasting, weather forecasting, all these can be used. And the main challenges with the scarcity of data. So with the growing availability of data as well as powerful and distributed processing units, deep learning architecture can successfully apply to major industrial problems. So however, deep learning is traditionally big data driven and lacks efficiency to learn abstractions through clear verbal definitions, if not trained with the billions of trained samples. So generally, if you are using a deep neural network, you have to provide a lot more information to train. Then only the device can itself identify the classes. So we need to provide more number of data. So generally, it's a big data process. And to make DL work with a smaller available data set, some of the approaches are generally is in use. First one is data augmentation. Data augmentation is if you have 100 images, but you need 1,000 images to process for training. So you can augment the data by flipping, slicing, or resizing, or rotating, or shearing. These kind of operations can be done. Basic geometrical operations can be done on the same image set, and you can augment. So the 100 image become 500 or 1,000 by using augmentation. This is one option to avoid this large data issue problem. Next one is, as I told, transfer learning. You can use the already pre-trained network, and you can use the same weights and bias for learning. Next is recursive classification techniques such as synthetic data generation. As we seen previously, the GANS, Generative Adversarial Neural Network, we can mimic the images or generate the images based on GAN network, and you can use that for training purpose. There we can call these images, generated images are synthetic images. And next is one-shot learning. It is another option. One-shot learning is also bring new avenues to learn from very few sample of training sample. So in one-shot learning, you can reduce the size of the network and become very small network, and you can learn the network with a very small amount of net data. So next is, I'm going to explain deep learning for image classification. So here we will see how we are going to set a deep learning platform for image classification. So deep learning especially take features from image automatically learn from the training process. So understand the problem in terms of hierarchy of concepts. So there are some hierarchy in the CNN design process. So each concept is built on top of the other. So here you can see it's a CNN with layers, input layer, hidden layers, and output layer. So the concept in the lower layers of the network encodes some basic representation of the problem, whereas higher level layers use these basic layers to form more abstract concepts. So that's why I told it is a hierarchical learning. This hierarchical learning allows to completely remove the hand-designed feature extraction process and treat CNN as end-to-end learners. So here we can see, given an image, supply the pixel intensity values as input to the CNN. So if I am giving an input to a CNN, I am giving the intensity values as the input. A series of hidden layers are used to extract feature from that input image. So these hidden layers build upon each other in a hierarchical fashion. So at first, only edge-like regions are detected in the lower layer of the network. So only edges will be detected. Next, the edges are used to define corners and contours. Corner means edges intersects, and contour means outline of the object. Next is combining corners and contours can lead to abstract, that is object parts in the next layer. So finally, you are getting an abstract of the original input image at the end layer. So this type of concepts, these filters are learning to detect are automatically learned. So there is no intervention by us in the learning process. So each hidden layer will learn and give us the abstract concept of the contents inside the image. So finally, the output layer used to classify the image and obtain the output class label. So neural network basics. So as we see, the human neural anatomy is shown in the figure, and the corresponding neural network anatomy is shown in the next picture. So here you can see each X is connected to a neuron via a weight vector W1, W2, etc., W4, and there is a weighted sum. After that, there is a step function. This is the activation function. So generally in human being, the action potential activates the neurons. Similarly, here also, once the weights are added up and weighted sum is obtained, you have to activate the CNN using an activation function. Okay, so then only your neuron will be activated. So the output node takes the weighted sum and applies an activation function and outputs a value. So expressing the output mathematically, you will typically encounter the following three forms. That is function of W1 x1 plus W2 x2 plus Wn xn, or generally you can say that summation of everything, or simply summation of Wa into xi. And next is activation function. So once we designed a CNN, so we have to activate the function. So generally there are functions like sigmoid, tanh, rectified linear unit, or leaky ReLU. So the best activation functions nowadays available is ReLU, that is rectified linear unit. So it will give only the values of x if x is greater than or equal to 0, and otherwise the function is 0. So it will have only a positive representation. So now we will see how the convolution operation is happening in a network. So in traditional feed-forward network, each neuron in the input layer is connected to every input neuron in the next layer. So we call this as a fully connected layer. However, CNNs, we don't use fully connected layers until every last layer in the network. So generally, all layers are connected, but it is not necessary that we have to connect every layer until the last layer. So we can thus define a CNN as a neural network that swaps specialized convolution operation in place of fully connected layer for at least one of the layers in the network. So here you can see, this is the structure of the CNN. Initially the input layer, inside the hidden layers, and finally the output layer. So here we will see now how we are going to design a convolutional neural network. So first you have to define the convolution operation, then followed by an activation function. So here you have to see the convolution operation. Convolutional neural network is doing nothing. The convolution operation. Here you can see I am taking a 3x3 pixel size and I am choosing a 3x3 kernel for my convolution operation. So this 3x3 kernel is nothing but an averaging kernel 1/9 into 11111. So I am multiplying or convolving with these pixels. I am getting a result as 132. This is nothing but multiplying all the pixel value with the corresponding mask and adding the values together and replacing the central pixel 252 with 132. Similarly, this will repeat for the entire pixels. So in other words, we can show through some simulation. So here initially I have a 5x5 image matrix having these values. I am choosing a 3x3 filter mask. This is my convolution operation. This is my convolution operation. You can see the mask is moving and you are getting the convolved result. So this is the initial input image size 5x5. After a convolution of 3x3, my size is reduced to 3x3. So here you can see the output dimension. Output dimension is input dimension minus kernel dimension plus 2 into padding by stride plus 1. Here stride is the movement of the mask along the direction. Here it is the stride is selected as 1. So that's why there is no padding is used. So you are getting stride is 1. So the output dimension is input dimension is 5 minus output kernel size is 3 plus there is no padding. So 2 into 0 by 1 plus 1. 1 is the stride plus 1. So the total size is 3. So that's why you are getting a 3x3 convolution. So because of this convolution operation, your input image size is reduced by a factor of 3x3. So here 5x5 is reduced to 3x3. If you want to get the same size 5x5, you have to use padding of 1. Padding of 1 means you are getting padding of 1 means you are getting 2 into 1, that is 5 minus 3 plus 2 into 2, same you will get, that is same size you will get. So if here we are using no padding, that's why we are getting 3 by 3. So this operation shows that whenever you go for a convolution operation, your input image size will be reduced. So now here we are using such more number of filters you can use. So here I am using, say for example, 4 filters I am using. So each filter having, say for example, 3 by 3 filter size, kernel size. So I am getting the first filter is operating on the image. I am getting 1 feature map. Second kernel is operating on the image. I am getting another feature map. Third is operating, fourth is operating. I am getting that much image feature maps. Make sure that here I am using M by M size. The size will be reduced either by M minus 10, M minus 5 likewise. So now after the whole convolution operation is over, I will get a lot of feature map as shown in the figure, and these feature maps will be stacked together. I will get a depth map. So after each convolution, I am reducing the size of input image. Say for example, from 5 by 5, it is changing to 3 by 3. If again I am giving a 3 by 3, it may reduce to 1 by 1. So the size of the image is reducing. At the same time, depend upon the number of the filter, the depth of the image is increasing. So that is the concept of convolution operation. So your depth information will be much more compared to height and width. So now activation layer. So after each convolution layer, we have to activate the convolution operation. So in order to activate the convolution operation, we have to go for here ReLU. So this is the, assume that this is the convolution result I am getting. And here you can see there are values like 1, minus 8, 12, 3, 3, 0, minus 6, 8, 1, 3, 2, 4, 2, 3, 4, 6. After applying ReLU, I will get a 4 by 4. There is no dimensional change. I will get a 4 by 4 with only activation functions which is greater than 0. That is, negative values will be 0. So this convolution layer is now activated. There is no dimensional change. Now we have to go for another layer called as pooling layer. Why we go for pooling layer is that, as we know, we are using deep neural network with a lot more layers and lot more images. Images may be having size of 100 by 100 or 200 by 200. So every time the CNN should process these large size images. So it will become more computationally complex. So in order to avoid the computational complexity, we are using pooling layers. There are 2 methods of reducing pooling. First one is the average pooling and second one is the max pooling. Average pooling will give the same pool size, but we are going for max pooling. So in our methodology, first the input image is given, followed by convolution. After ReLU, we have to go for pooling. Again, you have to go for convolution, again ReLU, then pooling. Then you can connect fully connected network. So there are 2 types of pooling, max pooling and average pooling. Here I will show the example of max pooling. So here I am selecting the previous case, 4 by 4 image after convolution and activation. Now I am choosing a stride of 2. Stride of 2 means, here you can see I am choosing a stride of 2 means it's a 2 by 2 matrix will be considered. In the 2 by 2 matrix, the first colored matrix, it will find the maximum value in the matrix. Which is the maximum value? Maximum value is 3. Next I am moving the stride by a value of 2. So these 2 will be avoided. It is moving to the next stride. Stride is equal to 2. So here I am checking for the largest value, that is 12. That is the max pooling, 12 value. Again, I am coming to the next 2 stride, 1, 3, 2, 3. So again, here the highest value is 3. And here again, moving to the fourth one, 2, 4, 4, 6, the highest value is 6. So from a 4 by 4 size image, using a max pooling of by 2 with a stride of 2, I am reducing my image into 2 by 2. So here there is a dimensional change. So the image size is again reduced by 2 by 2. So this is the advantage of using pooling. So here you can find the output dimension. Output dimension is input dimension minus kernel dimension by stride plus 1. So here you can see the output dimension is 4 minus 2 by 2 plus 1. Stride is 2. So 4 minus 2 is 2. 2 by 2, 1. 1 plus 1 is 2. So that is your final output layer is 2 by 2 size. The next is fully connected layer. So fully connected layers are always placed at the end of the network, and we don't apply a convolution layer, then an FC layer, followed by another convolution layer. So fully connected layers are applied only at the end of the network. So we can say that initially input image, convolution, ReLU, pooling, convolution, ReLU, pooling, then fully connected networks, 2 fully connected networks. So next is batch normalization. So batch normalization layer is another layer. In short form, we can call it as BN. The name suggests are used to normalize the activation of given input values before passing it to the next layer of input network. As we see, the pixel values are very high in nature. So in order to normalize it, we have to use a batch normalization layer. So that will reduce the pixel values to a normalized value. So that will also reduce the computational complexity. So batch normalization and pooling are the operation which is used to reduce the computational complexity. And batch normalization has been shown extremely effective in reducing number of epochs it takes to train the neural network. So this will reduce the number of epochs. So where we can apply this batch normalization? That is input image, convolution, ReLU. After ReLU, you can go for batch normalization. Then you can go for pooling. So next is dropout. So dropout is actually a form of regularization that aims to help prevent overfitting. Overfitting means, see, when you go for a training testing purpose, you train your data using 70% of information, and after of the 30%, you are using 20% for validation your model. So in your validating, you are getting less amount of accuracy compared to the training accuracy. So that means your network is overfitted. So in order to avoid overfitting, we have to use dropout. For each mini batch of our training set, dropout layers with the probability P randomly disconnect input from the preceding layer of the network in the network architecture. From this picture, it will be very clear for you. Here there is no dropout. This is the first fully connected network, and this is a second fully connected network. Here you can see there are 12 connections. Each and every nodes are connected together, but actually these connections are not necessary. Those are redundant connections. So because of that redundancy only, we are going to overfitting. So in order to avoid that, I am using a dropout of 50%. So here I have only 6 connections. From 12 connections, I am getting into 6 connections. Now these 6 connections are the only required connection which are sufficient for a classification. So this we are not deciding. This is designed by the network itself. One time we are running, this may be the connection. Second time it may be changed depending upon the learning process. So this is the advantage of using dropout. So it is common to place dropout layers with the P is equal to 0.5, that is 50% in between each fully connected layer. So now after including dropout, you can say that initially image, convolution, ReLU, batch normalization, pooling, fully connected, dropout, fully connected, dropout, then the final fully connected. There won't be any dropout because final fully connected layer is the classification layer or softmax layer. So there is no dropout we are adding in the softmax layer. So common architecture for training network. So here for convolutional neural networks are made up of primary layers, convolution, pooling, ReLU, and fully connected. So taking these layers and stacking them in a particular pattern yields CNN architecture. So once you studied about how to design an architecture, now you have to design your own network. So there are certain rules for designing your own network. So the convolutional and fully connected layers are the only layers of the network that learn parameters. And most of the common form of CNN architecture is to stack a few convolution layer and ReLU layers following them with a pool operation. So this repeats the sequence until the volume, width, and height is small, at which point we apply one or more fully connected layers. Say for example, general operation, we can say an input layer, convolution layer, and ReLU into n numbers, pooling m times, fully connected k times, then final fully connected or classification layer. Here, the star operation implies one or more, and the question mark implies optional operation. So here you can see the n is varying from 0 to 3. Maximum, you can put 3 convolution layers in a stack. That is the maximum condition. and m greater than or equal to 0, you can put more pooling, and maximum fully connected should be 2. That is restricted to 2. So whenever you are designing a convolutional neural network, you have to make sure that in a single stretch, you can put 3 convolution networks together. You can't put maximum 4. You have only 3 maximum. If you want to put another after these 3, you have to put pooling, then you have to put 3 more. In a single stretch, you cannot put 4 convolution layer together. So next is one of the simple architecture which is designed. I will show with example. Here I have an input image size of 32 by 32 by 3 because I am choosing an RGB image. That's why it is 32 by 32 by 3 RGB 3 color plane. So here I am giving a 5 by 5 convolution. 5 by 5 convolution means I am selecting a stride of S is equal to 1 and the padding of B is equal to 0. There is no padding. So after that operation, here we can see 32 minus 5. 32 is the original input size. 5 is my kernel size plus stride 1. So 32 minus 5 plus 1, 28 by 28. So 28 by 28 is the size of my output convolution. Now I am applying a pooling of 2 with a stride of 2. So 24 become half, by 2 become 14 by 14. So after a convolution operation and a pooling operation, I am converting my 32 by 32 image size into 14 by 14. And here this 8 represents the number of filters in the convolution operation. That means I have such 8 filters are there. That means the depth of my convolution operation is 8. Now again I am giving it into another convolution operation. So here my input image size is 28 minus 5 by 2 minus, sorry, plus 1. So it is 14. 14 minus 5, sorry, 14 minus 5 plus 1, that is 10. So 10 by 10, and here I'm using 16 filters. So here you can see 16 filters. So my depth image is 16, but the height and width is reduced to 10 by 10. Again, I am using a pooling. So pooling is a factor of 2. So 10 by 2, that is 10 minus 2 by 2 plus 1, that is 5. So I am having a pooling of 5. So my image output size is 5 by 5 with a 16 number of features. So here from a 32 by 32 image, I am reducing my input image size to 5 by 5 along with 16 feature map. So here this 16 represents the width of the image. That means that much stack of image features are available. Now you have to flatten. In order to give it a fully connected network, we have to flatten the entire thing into a single vector. So for that we are using one fully connected network or flattened network. So it will be total 5 into 5 into 1 is 16. So you will get that much values in a single vector. So then you can connect another fully connected. So in between you can connect any dropout so that the unwanted values will be removed. Now you have to give it to the softmax classifier for classification. So here I am choosing first FC is 120 and second FC is 84. So from this second FC1, 84 features will be taken for classification. So here I am downsampling by a factor of 1.5. So here I am getting 84 features, and 84 features will be given for softmax classification. So here I am getting a classification of either this belonging to a class A or class B. This is a simple CNN. You can try your own networks using the same design rules. And next option is multiscale CNNs are there. This is one of the network which I use. So here in multiscale means initially I have a 3 by 3 convolutional neural network followed by a max pooling, then again a 3 by 3 convolution network following by max pooling, and I have 1 by 1, 3 by 3 and 5 by 5. This is why it is known as multi-scale. Previously you can see you have only 2 convolution layer which is having same scale. Scale means 5 by 5 kernel size. But here you can see I'm using 2 3 by 3. Now I am using 1 by 1, 3 by 3 and 5 by 5. What is the advantage of this is that if you are going for multiple convolutional scales, you will get more depth information in your system. So after that, you can concatenate your features and you can connect it to fully connected layer. Then you can connect to dropout, then fully connected layer, then one more fully connected layer, then your softmax classifier. So this is one option, that is multi-scale CNN. And another one is multipath CNN. So in Multipath CNN, in previous case with the multiscale CNN, we have seen that we could get local structures or small level features when we go for more depth in the scale. But if you go for a global structure in an image, you have to go for multipath. That means once you find out your convolutional layer first, then after the first convolution, you have to provide a parallel path for another convolution. And then this is the primary path where we are having first convolution, second convolution, and third convolution. After that, you are concatenating the parallel path information. So make sure that when you are designing your network, both the feature size of the networks are equal, or size of the images are equal. Then only we can concatenate. After concatenation, you can go for flattened layer, fully connected 1, fully connected 2, and classification. The advantage of using for multipath network is that you will get global information of the image using this multipath. Previously, we will get only local feature. Now we are getting global feature. And finally, in order to get both global feature and local feature, you can combine these two, that is multiscale and multipath, that we will show in one of our application in the later slides. And next is the training and testing in deep learning. So in this process, first you gather, once you design the network, you have to gather the data set, the images themselves, as well as the labels associated with each network. For training the information, we have to label the data. Then only the machine identifies this data belonging to normal category or this data belonging to diseased category. So number of images should be labeled first. Then you split your data into training and testing set. So there are 3 design rules or splitting rules. The first one is either you have to split it into 66.7 and 33% 3 for testing, or you have to go for 75-25, or you have to go for 90 and 10. This is the standard splitting up of data set for testing and training. So this is a standard accepted around the worldwide. So now train your network. So goal is how our network learns to recognize each of the categories in our labeled data. So when the model makes a mistake, it learns from the mistake and improves itself. So once the network learned and it is finding and the data correctly and it is giving a good accuracy, that is known as the training accuracy. Now you have to evaluate your data set, that is the testing data. For each of the image in our testing set, present them to the network and ask to predict what it thinks of the label of the image. So in initial case, we won't give the label of the testing image. We will simply put the test image and we will evaluate how the network predict it. Then after the prediction, you have to compare your prediction with your testing label. Then you can say that how much number of tested images are correctly predicted. So based on that, you can have different parameters to. Hello? Yes, how many images we are correctly classified. So based on that, we have to analyze the performance of the network. So here the performance of the network can be analyzed based on confusion metrics. So here you can see there is an actual predictions and actual values, that is labels and predicted values. So there are 4 cases: true positive, that means actually is positive, you are expecting or predicting it as positive, that is true positive, that is the correct prediction. And the second one is false positive, that is we are actually is negative but you are predicting it as positive. And third case, you are expecting positive but you are predicting it as negative, that is false negative. And the fourth one is you are expecting negative and predicted as positive, negative. So this is true negative. So based on these 4 parameters, we have to find few parameters, that is accuracy, that is the ratio of TP plus TN by the total TP, TN, FN, FP. So this accuracy tells us immediately whether the model is being trained correctly and how it may perform generally. And precision is the ratio of true positive or the positive prediction values to the ratio of true positive and false positive. And recalls is also called as sensitivity. It gives the information about how efficiently the model reduces the false negative. This can be calculated as true positive by true positive plus false negative. F1 score determines the model's accuracy. This score gives harmonic mean of precision and recall. And it is a combination of recall and precision. And next parameter is we can go for ROC curve. That is a receiver operating characteristic curve. It is a graph between the true positive rate and false positive rate. And this curve has two parameters, true positive rate and false positive rate. So here, from this curve, we can find the TPR, that is recall, true positive rate and false positive rate. This will give you the performance of the classifier or the network. So the ROC curve plots TPR versus FPR at different classification thresholds. So we can see at different classification thresholds how much value we are getting. So performance analysis of the network. Another one is AUC, that is area under ROC curve. So another option to find the performance of the network is AUC curve. That means the area under the ROC curve. So for a value of 1, the prediction is 100%, and for a value of AUC 0, the prediction is 0%, or it is inaccurately predicted. And next is the set of pre-trained networks in deep learning. As you see, here I represented a lot of networks with prediction accuracy and relative prediction time using the standard GPU. So here you can see we are starting from the AlexNet to until the LastNet large. The AlexNet is giving only 55% of accuracy, which is trained on actually ImageNet dataset. These all are pre-trained networks, and these are having large amount of network structure and big in size. And from starting from AlexNet, SkuSnet, MobileNet, InceptionNet V3, NASNet large, up to NASNet large is getting an accuracy in the range of above 80%, but still it is not up to the system level performance. And next slide showing you the depth, size, parameters, and input size. So whenever you are designing a computer deep neural network, you have to make sure that your input parameter should be minimum and it should provide a maximum efficiency. So if you compare the generalized pre-trained networks, you can see the depth is starting from SkuSnet 18 to exception it is 71, and the size is starting from 4.6 to 85 MB, and the learnable parameters are in millions. And another problem is the input image size is already fixed, so you can't change the size. So you have to resize your image into these sizes in order to process. That is another problem. And next is another set of pre-trained networks. These are very large networks where VGG 16 and VGG 19. Here we have parameters in the range of 144 million. So these are the large parameter networks. So training these networks on our system is not possible. We need a high-end GPU-based system to train these networks. These are the problems existing with the pre-trained networks. And last is the public data sets available. These are the public data sets we can use for general image processing. And out of that, ImageNet is the biggest data set available. Most of these networks are trained on the ImageNet database. ImageNet contains different set of images except medical images. So the main problem we are facing in medical image processing is that we can't use the same pre-trained networks for medical imaging application because those networks are only trained on ImageNet nets, that is general images. So we have to either use transfer learning or you have to design your own network with the available GPU architecture. With this, I will wind up my session. First session. Next session is the application. So if you have any queries, you can ask now.
Dr. Varun,
yes.
Shall we complete the other one and have a final
of course,
discussion session? That will be fine, I think.
Okay.
Participants, you feel free to ask any questions to the speaker. There is no such thing like out of scope question or something like that. So you can feel free to ask any questions to him. So to the maximum possible, here the speaker will be answering or clearing all your doubts. We understand that you are from basic, intermediate, and expert categories. So basic people, you can ask any questions related with AI and deep learning or image processing. You will get the answer. Please feel free to ask questions in the question answer session.
Sir, screen is visible.
Yes, Varun. Yes.
Okay. So next we are going to see some of the applications. Due to lack of time, I only prepared a few applications which we have done. So the first one is deep learning for computer tomography. So as you know, the lung nodule classification on computer tomography is a tedious task. So the CT will helpful in reducing this lung cancer if you detect it early. So because it is high sensitivity to detect lung nodule and easy to locate lung nodule. So here you can see the picture, the benign nodule and a malignant nodule. If you look at these two pictures, we can see that most of the both of these are look alike. But we can't say that simply looking at the picture, whether it is a malignant affected or a benign normal. So similar visualization is the problem here. So we have to detect it correctly using a deep learning network. So according to Semien National Lung Screening Tail, screening CT can reduce lung cancer health in 20%, but 96% of nodal findings showed a false positive because exactly the same visual representation, some of the finding may be wrongly interpreted. So we have to make a better decision because it's a medical case using the deep neural networks. So for that, you have to use a better images with the help of a clinician to go for the training purpose. So here we are proposing one CT lung net. So here we are using deep learning for classification of less than small 2 cm pulmonary nodule on CT images. So here we have a 3 convolution neural network. The initial network is a 5x5 network, then pooling of 2x2. So that's why you are having 64x64 image size. That is reduced to 60x60 with having 12 feature maps. Then by using pooling, you are getting 12 feature size with 30x30. And again, another convolution by 5x5, you are getting 24 feature map with 26x26. And by max pooling, you are getting 24 features at 13x13. And again, convolution using one more, then you are getting 9x9. That is 48 feature map at 9x9. Then these 48 feature maps will be used for classification using a fully connected network and a softmax classifier. So here in this work, we have used a patient database having training data set of 77 malignant and 90 benign, and a testing set consisting of 31 malignant and 29 benign. So here, this is a very small network. That's why we are using this much very small data set. And here we have 4 categories of test results with the category. First one is C1. So this is human reviewed category. That is an expert reviewed category. So highly suggestive for benign C1. C2, benign more likely than malignancy. C3, malignancy more likely than benign. C4, highly suggestive for malignancy. So these are the 4 categories by human reviewers looking at the images. So another option is using the CT lung net decided output. That is another second reviewer. The test result with the category and a CT lung net result. So both are done by the human reviewer and finally giving the final results of C1 to C4 category. So if you look at the next slide, the CT lung net shows a higher AUC of 0.85 and 0.82 from this picture. So this will show the comparison of the AlexNet, that is a pre-trained network, and CT lung net. So here you can see the blue one represents the CT lung net result of the sensitivity and specificity, and AlexNet represents the green one. So you can, from the picture itself, we can see that the specificity and sensitivity provided by the CT lung net is better compared to the pre-trained network. That is the advantage of our own network compared to pre-trained network. And on the second graph, we can see the test one is independent observer performance without aid of CT lung net. That is simply people are two students and two physicians are corrected the data set, checked the data set, and they given the result. Their accuracy is in the range of very small, 60, 50 likewise. But on the other hand, the red one, second is test 2, observer performance test with reviewing the CT lung net malignancy prediction rate. After reviewing with the malignancy prediction rate by the CT lung net, then the people predicted the result. That is shown in red color. You can see that that is much better compared with the previous one. So we can say that the deep learning kind of networks will definitely help improving the physician to make a decision. This is an outcome from this work. And these are some of the reference is missing, sorry. So next one is deep neural network for computer tomography. This is another network. In the previous network, I have said we can use both multipath and multiscale neural network for operation. So here we are using the proposed convolution neural network. Here we have an input image. It is having a 7x7 convolution with 12 feature maps. After that, there is a pooling, then a 7x7 feature map, 7x7 convolution with the 24 feature maps, and a pooling of 2. Then you have MS-conv. This is nothing but multi-scale convolution. That is, you are having a multi-scale convolution network, 3x3, 5x5, and 7x7. Previously, up to this layer, we have only 2 7x7. But from here onwards, we have 3 depth information available. That is 3 scales, 3x3, 5x5, and 7x7 available. Again, we are having one more 3x3, 5x5, and 7x7. So we have 2 multi-scales. Then we are concatenating this to the layer. And on the same time, you have a multipath layer. From this multipath layer, after the first convolution, we are taking a multipath with a convolution layer of 11x11 and a pooling of 4x4. Why here I am choosing pooling of 4x4 is that in order to make the size of the image to be cop up with the image size of the multiscale. And here I am using no pooling is used in the multiscale. And then you have another doubt. Why you are going for low values of scales in 3x3, 5x5, and 7x7, and in multiscale and in multipath you have 11x11. So whenever you are going for global information, in order to get a global information, you have to go for large size of convolution. That is why in multipath we are going for 11x11, and for local structures or fine structures we need smaller convolution. That's why you are going for 3x3, 5x5, and 7x7. So using this LangNet. Here we compared some of the result with the existing methodology. The proposed method with the multiscale plus multipath is giving 90.35 or 90.38 accuracy and a sensitivity of 88.7 and a specificity of 92.4, and the area under curve, that is AUC, is 94.8. So this is better compared with the previous works because we combined both multipath and multiscale architecture. Here also you can do neural networks. You can go for either 1x1, 3x3, 5x5, or you can stack one more layer. But make sure that when you add more than one stacking of layers, the learnable parameters will increase. So when you are designing your network, make sure that you are having less amount of learnable parameters so that your system can efficiently learn the network. If you have a good GPU-based system, you can do the process. And next is the references for this CT work. And the next is deep learning for ultrasound images. So next work is breast lesion classification on automated breast ultrasound. Nowadays, the main works are going on ABES database. ABES is automated breast ultrasound. It is a non-radioactive and used as supplemental screening for breast lesion detection. It is compared with mammography. Screening ABES will take a lot more time because it is a slice-by-slice scanning of the breast. Here in the picture, you can see there is a transverse view and a coronal view of the picture, where a red line marked, red square is marked. This represents the benign cancerous cells of this breast. So here we are using an inception V3 using transfer learning. So here we can see the inception present V3 backbone. We have 2 convolution networks and 1 pooling there, then 3 convolution networks and 1 inception A, 4 inception B, and 2 inception C networks. And in inception A network, see when I told about the learnable parameters, if you use a normal 3x3 5x5 convolution here, you have 5 square, that is 25 multiplications will be there. So in order to avoid that, we are using 2 3x3 convolution. So a stack of 2 3x3 convolution will help providing the same 5x5 operation, and also because of this 3x3 operation, you have 3 square 9 plus 9, or totally 18 multiplication will be there compared to 25 multiplication of 5x5. Similarly, here 7x7 can be replaced with the 7x1 and 1x7 convolution. So in effect, it will be 7x7. So likewise, in this inception at V3, we have inception V3 can be 3x3 can be also split into 1x3 and 3x1. So by splitting it into 1x3 and 3x1, 1x7 and 7x1, we can reduce the number of learnable parameters. And we are using the same network which is trained on the ImageNet data, and we are obtaining an accuracy of 78%. Here we can see the accuracy obtained is 78%. The accuracy is less because we are using transfer learning. That is, we are using the same learned weights for testing the medical image data set. And next option is we can go for two more options. The breast cancer classification ABS using multi-view CNN with transfer learning. In multi-view CNN, what we do is we will do operation with the two images at a time. That is, first we take the coronal view, then we take the transverse view. The first is the coronal view slice, and the second we take two transverse view. We will stack it together to form a size 229 229 by 3 size, and then we are giving it to inception backbone. Then from the average, global average pool is the pooling layer, the final pooling layer. From the global average pooling layer, we are taking the feature, and then we are connecting it to fully connected layer of 256 size. Then we are giving a dropout, removing the unwanted connections, again giving it to 128 fully connected, then again dropping out and removing unwanted connection, then it is given to the fully connected for classification. So here we are connecting only, checking only two options, either it is a disease or not. That's why your fully connected network having value 2. And the second option is multi-view strategy B. Here we are using first the coronal view, then the transverse view. Separately we are giving through two inception backbones, and separately giving data from two global average pooling, then concatenating at the fully connected layer, then again the same process. So here we can see what is the result of these two, A strategy and B strategy. So in this case, we can compare the work with a different inception V3 with the transverse view only, coronal view only. In ResNet 50 with the multi-view strategy, it is 80%. Inception ResNet V2 with 0.87. Inception V3 with the first strategy, that is A strategy, it is getting 88.5. But with the multi-view strategy with the B, we are getting 85.3. So the best option is, for getting a better accuracy, you have to go for the multi-view strategy A. So from the proven results, we can see that the multi-view strategy A is best in ultrasound imaging classification if you use a transfer learned inception with network. So next is ML and DL for early detection of ankylosing spondylitis. I think you people are heard about a disease, spondylitis. It is a disease happen to the sacroiliac joints. So it is a kind of arthritis. Arthritis affects the sacroiliac joints. It has an average diagnosis delay of 7 to 10 years due to its unfamiliarity of a disease outside the musculoskeletal radiologist. Initially, we are unable to get the information. Later only, it will affect our body. So from an abdominal pelvic CT scan, this shown in the left picture, can erosion be differentiated from the control patient? So this is an abdominal pelvic CT scan. You can see that there is a yellow marking. So this yellow marking, you can see there is a small portion. So that portion is taken and given on the right picture. So here the first one is erosion, early ASM, that is ankylosing spondylitis symptom. Here you can see there is some erosion happening. For a young control patient, this is very clear. And for an old control patient, this is more separated. And it is erosion is much more. So this is the three options. If you want to classify this, you have to give 3 different kind of images to the network and train the network. Then the network knows that whenever the image comes, this is belong to early, this is belong to young, this is belongs to old. So this is actually using machine learning, the differentiation of ankylosing spondylitis using machine learning, that is random forest classifier, with GLCM and LBP, that is local binary pattern taken feature data. That is 8 feature from both LBP, 4 from LBP and 4 from GLCM. And it is given to a random forest classifier using 8-fold cross-validation. So here the erosion versus young control, we are getting an ROC, mean ROC in the range of 97. And for erosion versus old control, here you can see a mean ROC of 0.91. And the chance of getting this disease is shown in the red color. And next is using DL, the differentiation and therefore diagnosis is even better with deep learning. In machine learning, we could get only this much accuracy. So we need to improve the accuracy in case of old control, because in old control, we are getting an accuracy in the range of AUC in the range of 91 only. So we need to go for deep learning methodology. So here we are using inception v3, the same inception v3 with 8-fold cross-validation. Here what we do is, instead of going for normal classification, we are going for global average pooling. After global average pooling, we are dropping out, taking the fully connected layer output, giving a ReLU to the activation function to the fully connected. Then from the fully connected layer, features are directly taken instead of sigmoid and doing 10-fold cross-validation on the classification. So here, in this case, we can see that we are getting an accuracy of 97% for using an 8-fold cross-validation. When you have a doubt that what is 8-fold cross-validation, if you are not having sufficient data for training and testing purpose, or if you don't have test data, you can do a 10-fold or 5-fold, 8-fold or 10-fold cross-validation. And if the data is imbalanced, say for example, your class A is having a category of 1000 images, class B is having a category of 500 images. You have different data imbalance in data. So in order to avoid this data imbalance, you have to go for cross-validation. So in cross-validation, what we do is, for in 8-fold cross-validation, the data set is divided into 8 categories, and one time 7 category will be trained and 1 category will be tested. Next level, that tested category will be put into the training, another category will be taken from the training, and it will be done until the 8 categories will be tested and trained. In 10-fold cross-validation, the category will be split into 10, the same process. So here we can get overall performance of the network if the data is unbalanced. So here we can get a classification accuracy of 97 for erosion versus all control. Erosion versus all control. Previously we have erosion versus young and previous control. Sorry, young and old control. Here for all control we are getting an average accuracy of 97. So compared to ML work, DL is giving a better accuracy. That is the advantage of DL in this application. And next is RIP tracking, labeling and classification system. So keeping track of RIP, that can be a tedious, time-consuming and potentially error-prone task for a radiologist. Can you keep track of the counting? Is there an easier way? So we are looking into this, and the labeling system uses computer vision to locate and track RIP candidate regions from actual CT scans with the window size and level at 727 and 560 respectively. So here you can see initial one is the original scan, and the second one is the video. You can see the modified scan where the RIPs are clearly visible. So from this, the RIPs image, we have to detect the RIP and find out, classifying which are the RIPs having problem, and then we have to mark it. So in a 3D image, we have to 3D video, we have to mark all these things. So this is the main problem we are associated with this kind of RIP tracking and classification. So this is the full view of that 3D structure of the RIP. So now we can see how we can do this process. So initially we can combine both normal process and image pre-processing and deep learning process. So here the steps 1 to 4 are the pre-processing steps, and image stage 5 is utilizing the deep learning. So first we are extracting the RIP candidate region and the shape and the size and represent them as a centroid and bounding boxes. Second is, for each frame, combine sufficiently close centroids. And third, for each frame, for each centroid, trace the centroid movement by finding the closest centroid, next frame, and over a period of 3 frames. So because we need to design the next frames. So the fourth one is varying post-tracking refinements and heuristics. And fifth, labeling and classification of bounding box using deep learning works. So now you can see this is the steps we are using. Stage 1, edge detection. Stage 2, morphology. First you are getting, this is for a slice image from that 3D view. From a slice, we are getting the edges. Then we are having a morphological operation, maybe erosion, dilation, whatever it may be. Then stage 1, contour detection. Then region detection. Then centroid tracking, finding the centroids. Then finally the labeling and the classification. Labeling and the classification is done by using deep learning methodology. So how you are going to label and classify? Once you obtain the centroid and marked the label, it is labeled. Now you have to check whether the area which we selected, that is the region of interest, are having any fracture whether it is an acute fracture, whether it is an old fracture, or it is a regular portion. So for that, we have to use deep learning. So feature classification using deep learning classifier trained via transfer learning, again inception v3. So in order to familiarize with the same network, we are using the same inception backbone here. So here we are using inception backbone v3 and fully connected network, activation function using ReLU, then batch normalization, then dropout by 0.5, then fully connected, then ReLU, global average pooling. From the global average pooling, we are taking the feature, dropping out, fully connected, applying ReLU, then giving the softmax. Here we have three. Why we have three is that we have three category of classification: acute, old, and regular. So we are getting the result here. This is the confusion matrix. Here acute is we are getting 90%. Old is getting 89% classified. Regular is getting 99% classification. Most of the regular RIPs are classified correctly. Old is corrected as 89 and acute is 90%. This is the number of samples or number of layers correctly classified. And this shows the average value, that is weighted average values. Weighted average values, precision is 95, recall is 95, F1 score is 95, and support is 20,640. That is that much sizes we have used. So here we can see a video which is showing the entire process, that is detecting and marking. So here you can see the detecting and marking shown in figure. Green is the original good one, blue is the acute one, and red is the diseased one, fractured one. Here you can see after applying the deep learning algorithm on the video set which we seen earlier, we can correctly identify where the problem happens. I will run it once again. Here you can see we can exactly mark where the problem happens. So the clinician have now very easy to find where the problem happened exactly. So he can give a suggestion, or he can look at the slices at which slice the problem happened. Only the slice he can look at very clearly instead of moving through the entire 206 slices. So next other applications, say for example, we have different applications like license plate recognition, general applications like license plate recognition, then crop yield prediction. See, nowadays generally there are UAV based techniques are there, that is unmanned aerial vehicle, drone based techniques. So drone based techniques can be used for in defense and in agriculture. So agriculture field we can go for crop yield prediction, then the crop growth prediction can be done using deep learning, then medical image segmentation, then osteoporosis detection, that is it's a kind of deformation happens to the human bone. So that kind of detection, then phase super resolution, then forgery finding, then veterinary biomedical application, security system. There are a lot more applications of deep learning. Due to lack of time, I am winding up with this. If you have any doubt and queries, you can ask. Not only we are limiting into its application into these areas, there are a lot more application. There is a lot more thing to explain in medical imaging itself. So as of now, I am winding up. If you have any queries, you can ask now.
Thank you very much, Dr. Varun. It was a very interesting and informative session. Specifically, I could see a complete flow in your presentation. The way how a beginner should learn to start with artificial neural networks and how should they go into deep learning in a step-by-step fashion. That is really amazing. And the way one of the main objective of this workshop is to make sure the participants do hands-on training, or they need to do the practical implementation. I know deep learning, the word sentence may not be correct, only if you have some deep understanding into the concept of deep learning. That also you satisfied. And when you come to the last stage, the application parts, that is very interesting, because normally people go for the high class images like brain, kidney, liver. But the things you talked about, the ribs, the mucoskeletal images and the spondylitis, that is very, very interesting. And I hope our participants also would have got some useful information out of that. Now, without wasting time, we'll go for the question and answer session.
Yes,
we have 40 minutes time. I request, if possible, the participants to come directly to the Zoom to interact with the speaker and ask your questions. that will be much more better for you to clarify the doubts, because when we ask a question, there may be a sequence of questions which you need to ask to make sure the speaker give the correct answer. So it will be fine. I request Dr. Anushya to take over the question answer session.
Yes. So participants, if anyone would like to directly ask your questions, please go ahead. Otherwise, please post your questions in the chat window and I will read it out to Dr. Varun.
Varun, you can stop sharing your screen, I think.
Okay, okay.
We have a question, sir. Which learning procedure is good for image processing, supervised or unsupervised?
It is actually two things. Mainly, see, supervised learning is mainly used for if you have a image with the labeled data. Generally, you are going for a deep learning kind of networks. You are better to go for unsupervised, because your system should learn it and tell you the answer instead of giving an answer and learning. It is better to go for unsupervised learning. Initially, you can learn. Initially, you can learn your system with the supervised. Then later, your system has to be unsupervised one. Or you can go with the semi-supervised. Nowadays, people are using semi-supervised. Half supervision along with the unsupervised. So better to go for semi-supervision. Because as a beginner, you may not be fully known about unsupervised learning. But generally, if you have an autonomous system, in developing an autonomous system, it is better to go for unsupervised learning.
The next question, sir, is sigmoid activation function is used if output layer has 1 neuron. Softmax is used if output layer has 2 neurons. If the output layer has 3 or 4 neurons, which activation function is better?
So softmax is also better. See here, if you have, I don't know whether these people are having any idea about Python coding. So if you go for this coding, you can see that there is a cross entropy loss function. So the classification is based on cross entropy loss function. So if you go for a binary classification, you have to choose binary cross entropy. The loss function should be chosen as binary cross entropy. And if you have a multi classification, you have to go for categorical cross entropy. Then your softmax will classify it into multiple classes.
The next question is, will you suggest a suitable CNN architecture to work with text images?
Say, for example, you can use any of the pre-trained networks, or you can design your own. That's why I given a session on designing networks. Better to use your own networks, because the pre-trained networks, as I told earlier, having a huge amount of bias and weights, and you cannot run your data on that network on your normal system. So better to use your own networks. As I told earlier, multi-scale is there, multi-path is there, or you can design your own networks and use it. That is better, because pre-trained networks I am not suggesting to use.
Hello.
Yes, sir.
Yes, ma'am.
Sir, I have one query.
Yes.
Sir, while downloading the medical data set for brain tumor imaging,
Okay.
several data sets are having in DICOM format and .NNI format and some other format, .mat format and all. How can I give all this data to the CNN network, sir?
Yes, you can give. See, there is a NIE reader is there in Python. If you are coding using Python, you can directly read the NIE file.
Because for training the CNN network, we need large number of data. Many data set we need, sir.
Yes.
So if I particularly choosing .NNI format, is
See,
it enough to train the CNN network?
Generally, .NIE file will be of 3D structure. That's why. So you are getting a voxel, not a pixel. So you are getting voxel data. So NIE is 3D. So you have to either read it in your using Python codes. You can read it in network, and then you have to slice it and use the images. Otherwise, you have to go for 3D CNN. If you want to process the NIE files, you have to go for 3D CNN, 3-dimensional CNN instead of 2D.
Would anybody else like to ask a question?
Good afternoon, sir.
Yes, definitely.
I was the one asking about that CNN architecture, suitable architecture for text images.
Yes, yes.
And when I
You can use tell me.
Many of them they said instead of going for designing your own architecture, go for transfer learning.
Yes, yes. See, transfer learning you can use. The thing is, if your image is tested on, first of all, you have to check on ImageNet database. If your kind of images are already trained on the network, then you can better to go for transfer learning or the same network. Generally, for medical imaging cases, the medical images are not available in the ImageNet. So that's why I prefer to design your own network. If your data image is available in the ImageNet set, you can definitely go for transfer learning with the existing networks. But choose very simple network. Don't go for higher networks because it requires a large amount of GPU to process your data.
But is it easy for us to design our own networks, sir, according to our application?
Yes, yes, we can do.
Okay, fine, sir.
See, that is a novelty. That is a novelty part from CNN. See, CNN is doing all the process for you, right? Then what is the novelty? Novelty is the design what is contributed by you.
Okay. Thank you, sir.
For ARMD classification. Hello, yes.
Arun, and the novelty in terms of number of layers, or it's about the activation function what we use? Yes. It's about the structure, right?
It may be structure, it may be activation function, different combination we can put.
Combinations, yes.
Yeah.
Okay.
But we should make sure that it should give an edge over the other.
Yes. Okay. Thank you.
Okay. So there is another question for ARMD classification. Any database available? Yes, there is a dataset called Menly dataset. It is having 83,440 images, which is having Drusen, that is dry AMD, choroidal neovascularization, CNV, that is around 37,000 images. The normal images of 23,000 and one more image, Drusen is there. So 4 set of images are available. Menly dataset. You can refer that for ARMD, age-related macular degeneration datasets. If you are looking for OCT. For fundus, there is an OTDR grand challenge is there. If you want to, anybody can register on grand challenge. In grand challenge, different challenges are coming. Expired challenges are also there. In expired challenges, the datasets are available.
Sir?
Yes.
Sir, could you please suggest some metrics?
What?
Performance metrics, sir.
Performance metrics, that's what I explained earlier. You can go for accuracy, precision, specificity, sensitivity, then ROC, region under curve, area under curve, all these things can be used. AUC will give the accuracy of the system.
Okay. Sir.
We can also apply CNN for, there is another question, CNN for phase resolution. Yeah, super resolution we can use. That's what I told. See, when you go for the adversarial GAN network, that is generalized adversarial GAN network. In generalized adversarial GAN, we have 2 networks, generator and discriminator. In generator, we are giving the low resolution image, and then we generate one image and giving it to the discriminator. Then the discriminator compare it with the original image, and then it will predict the difference or loss. That loss will be given back to the predictor for generator for generating the image based on the loss. Once the loss is penalized, we can say that the discriminator will make a more closer image. So using that GAN network, we can easily go for super resolution.
Hello.
Yes.
Sir, if I'm using .map image formats, whether it is compulsory to convert it to JPEG or a PNG image to give
No, you can read it in Python, no problem.
.mat also we can read.
Yes, .mat also we can read. Yes. The format is not a problem in that.
Okay. Okay, sir.
Dr. Varun, I have a small question. Like, suppose if they are using a MATLAB 2019 version, I think the possibility is there.
Yes.
But if the medical images are in DICOM format,
DICOM reader is there, sir. In the latest versions, 17 onwards, DICOM reader is there.
Okay.
Otherwise, they can simply take it. Codes are available in Google to read the DICOM datasets. It's a DICOM read. That is the function. In MATLAB, it is DICOM read.
Sir, we can use DICOM in Python.
Yes, yes.
To read the DICOM images.
Yes, yes. It's easy to use in Python compared to MATLAB. MATLAB, you have functions are available. And the second thing in MATLAB, you have deep learning to be used. You have to use from the latest version 19 onwards, and you have to install the deep learning toolbox. And if you want to use any pre-trained network, you have to download all the pre-trained network on your deep learning toolbox. Then only you can use. Similarly, for Python also, you have to download all the networks. It is having only MB size. You can download it and use. Data augmentation, another question, data augmentation, no libraries available. You can use data augmentation. Say, for example, in case of an image, you can take the image, you can flip the image, rotate the image, you can shrink the image, shear the image. So likewise, you can do the augmentation. So rotation means 10 degree, 20 degree, 30 degree. That itself give you more representation.
Hello, sir.
Yes.
This is Piyush Raja.
Yes.
Why it is called deep learning?
Because you have more number of layers inside, hidden layers. It's going very deep. See, if you look at the picture which I shown earlier, if you look at the most of the pre-trained networks, you can see the layers are, say for example, for RusNet, it is 1202 layers. Can you assume 1202 layers? So this much deep it is going into the image. When you're giving an input image to a RusNet, it is going that much deeper. That is why it is known as deep learning. You have more number of hidden layers. And if the number of layer increases, the requirement of data is also increasing.
After this workshop, some of the participants may develop a deeper network also. That is also possible with your very good lecture.
Thank you, thank you.
Hello, sir. Good morning, sir. This is Irango from Nanda Engineering College, Tamil Nadu.
Yes, tell me, sir.
Sir, how we can implement the deep learning in IoT, sir? I'm planning to do research, sir. I'm going to apply deep learning in IoT. What is the process, sir?
Okay, see, you can either hire a cloud. Okay, you can hire a cloud and say, for example, for a medical decision kind of thing, you can ask the doctors to provide the data set, and the data set can be deposited in the repository over the cloud, and you can access the data at any time, and you can use deep learning networks on those clouds, or otherwise you can go for Google Colab. Google Colab is it's a cloud service. There you can use the data set for processing.
Okay, sir. Thank you, sir.
There is another question. Lung CT images are 3D. It is right to use 2D slices for lung nodule classification like benign and malignant. Yes, you can use 3D image can be sliced and you can take the slices to get. The option is if you want to go for a better perception, you have to go for a 3D convolution so that you will get a better structure of the object. You can go with either 2D or 3D. And there is another question, is there a maximum number of hidden layers in deep learning? There is no restriction. You can decide whatever depend on your system requirement. Any other tool for image conversion? Image conversion, see, all the image converter for MATLAB is available in Google. Similarly, in Python, you can easily convert the images into whichever the format you want.
We have another question, sir. Can we use ELU instead of ReLU for image segmentation?
You can use. It is depend up to you, but preferably we are using ReLU because we are having a better results when we go for ReLU. That's why. You can use, but the thing is, why you are using ELU? There should be some reason, right? So you have to try your own all the possible activation function and choose which one is apt for your application. It depends on application also. For classification kind of thing, ReLU is best. So if you want to choose ELU you can use, but at the same time you have to try out all these activation functions and see whether it is coming correctly or not. In unsupervised learning, there is one question previously, unsupervised learning can be done. Yes, unsupervised learning can be done. Mainly unsupervised learning, we are going for clustering kind of thing, because we doesn't know the label of the image. So we have to do a clustering operation based on the size, shape or feature. We have to cluster it. Say for example, K-means clustering. Those kind of works are clustering, that is unsupervised learning. So we are doing and telling. But the same thing can be applied in learning also. Deep learning, if you give an unsupervised learning operation without labeling, then network will learn and predict whatever it
Swami.
Yes. Hello.
Dr. Abdo, continue.
Yes. Okay, then another question, which technique is suitable for liver tumor segmentation, detection and classification? See, you can use both deep learning for detection and classification. So for that, for detection kind of thing, you can use some of the existing method like SSD or YOLO-V or faster RCNN techniques are there. RCNN means if it is a video sequence or 3D, you can go for RCNN. As I told earlier, RCNN can be applied with video sequences. You can go for RCNN.
Dr. Sendil Kumar has raised his hand. Dr.
Okay,
Sendil Kumar.
Yes. Dr. Sendil Kumar or Dr. Sherry Garg? Anusha, meanwhile, you can read the questions in the chat.
Yeah, sir.
Data set to predict yield prediction for agriculture. Some data sets are available, but mainly we are having collaboration with the University of Saskatchewan, Canada. From there, we are getting the data. So mainly you can search on web. There may be a lot of agricultural data sets available.
Sir, another question is it compulsory to use flattened layer before the first fully connected layer?
Because we need to flatten the data into one vector. Because we need to flatten the entire data into one vector, then only we can predict. That's why we are converting it into flattened layer. Otherwise, it is an image, right? Image size of say for example 5 by 5 by 5 by 5 by 48. So 48 feature maps will be there. So that 5 by 5 should be converted into a vector. So that's why we are going for flattened.
Dr. Subha Rao has a question, I think.
Okay, there is one more question. Will the dropout process affect the accuracy? See, the dropout problem means, see, if you are not using dropout, there may be chance of overfitting. See, your fully connected layer is, as I told earlier, connected to most of the connections in the next layer. So some of the connections are actually unwanted, not necessary. So that may use some of the data. So the problem is we need to provide only the mandatory connections. So if you use dropout, you will get better accuracy. Otherwise, the accuracy will reduce.
Hello.
Yes.
Sir, I am speaking from Tirunelveli.
Yes.
Sir, as of now, up to how much depth we can go in deep learning in regard to hidden layers?
How many?
Up to how much depth we can go? How many hidden layers I can have?
You can have more number of hidden layers, madam. It depends on your application. And the second thing is you can go for more hidden layers, but the thing is you have to think about the parameters which your system need to be learned. So you have to minimize the learnable parameters. So it should be giving a better accuracy, then you can stop with whatever the layer you have decided.
Okay. Is there any specific validation process for my?
It's actually validation is there, madam. Actually, out of the 75 and 25 data splitting, the network itself validate first. You can see the network accuracy. You can give out of the 25% testing data, you can put 15% data for validation. So on 75 it will test train, then it will test. Then you have to test the balance 10 with the testing.
Oh, thank you.
Okay.
We have a question, sir. Kindly specify some techniques about signal to image conversion.
Signal to?
Image conversion.
Signal to image conversion. I didn't get.
Dr. Leena, could you please elaborate on the question?
Dr. Leena, can you please come to the live Zoom and ask your question? Dr. Leena?
Excuse me, this is Jenkins.
Yes.
Related to dropout, are there any method to choose which node to drop, or is it a random way of selecting the dropout?
See, actually, we have to apply only dropouts in between the last two fully connected layers. That is a rule. And second thing, we are putting dropout because of that. We are not deciding. The network itself decides. That's why I told earlier. Once during the first time of iteration, the networks may give, say for example, first 6 layers. It depends on its activation. But next time it may not be the same 6.
Okay.
It is decided by the network. We have no, we are not intervening on that operation. The network itself learns.
Okay, sir.
And Dr. Varun, I think Dr. Leena asked about, is there any necessity for converting a signal to image?
No,
Maybe
no.
she may have a data, I guess, with
No,
signal.
no, no need. You can go for one-dimensional convolution with the signal. One-dimensional convolution can be used with the signal.
We have another question, sir.
Yes.
What are various deep learning techniques that can be implemented for image datasets other than CNN?
Other data. So see, we have CNN along with the RCNN is there, then deep belief networks is there, then Bayesian deep learning is there, then reinforcement learning is there, then adversarial learning is there. Adversarial learning, the thing is that if you have less amount of data, you can take an image, add more noise, or add some discrepancies to the image, and you can do the process. That is adversarial deep learning, adversarial learning. These are other learning methods.
Then we have, please explain about the time series modeling and recurrent neural network and where we use them.
Recurrent neural networks?
And where we use them.
The recurrent neural network is mainly used in video processing. So in recurrent neural network, as I told earlier, we have different time series, right? So at time 1, we can put 1 sequence, time 2, we can put 2 sequence, 3, we can put 3 sequence. So we can easily put different slices at the same time. And at the same time, this can process in parallel. So RCN is better for video processing.
The next question is, can you please tell me what technologies I should learn to do research using deep learning, because I'm a mechanical engineer, like Python, Java, image processing, what area should I have deep knowledge?
So you should learn about Python. Python you have to learn. Along with that, see, better you have to go for some courses in Coursera, advanced deep learning courses available in Coursera. So you can learn that. In that program itself, they will give you both assignments and hands-on session. So it will be very useful for you. If you do some 2 certificate courses, maybe 2-3 weeks duration, you will be very good in this.
The next question is, if you're not going for testing, is validation enough?
Validation, see, validation means you are only validating your model. You have to test on other data, then only you can say that your model is working. Otherwise, you validated on data, but your model is not even tested. It should be tested with unknown data, then only you can say that it is predicting correctly. So validation and testing is very must. And I can see one question, please. Suitable laptop work with deep learning. See, generally we are using desktops with GPU. I am using a system with Threadripper Ryzen AMD processor with 11 GB of 211 GB of GPU. That is RTX NVIDIA RTX GPU 1080 GB. It is around the cost 3.6 lakhs. And you can use almost laptops with 70,000 or 1 lakhs. I think 1080 7 GB, 6 GB laptops are available. That can be enough for normal, simple design. Or else it's better to use the Google Colab. It is freely available. It is a 12 GB of GPUs available with Google Colab. You can register and you can use the Google Colab. It's a cloud platform. So you can use over there. But it will take some time, but it's better.
Is there any skin disease detection system using deep learning?
It's already there. Melanoma detection is already been there. But the thing is, see, things are already been there for a long time. You have to apply your knowledge and do something differently. That's what the thing. You have to design differently. Collab you can test. Better for research means you have to go for your own research setup. You can test your basic thing on Collab because it may access different people. There may be chance of fraud thing may happen. So be careful. But as of now, you can, as a learner, you can use that.
There's a question on the significance of deep learning in question answering applications.
Yes, definitely there. Because in terms of robots, if we program a robot using deep learning methodologies, we know there are AI robots are available. So there it's a very important component for this. We can implement this kind of applications there. So there we have to train with the different, the tedious thing is training process here. We have to train with all the possibilities. Otherwise, we have to make, give more artificial intelligence to the system so that it can learn and tell.
The next question is, can we use web data for our research application or should we gather real-time data?
Whenever you are taking data, web data can be used, but the thing is you have to go for a standard data set. Otherwise, it is not useful. Because you need to compare your work with, whenever you are submitting a paper, they will ask you to compare with the state-of-art methodologies. So you have to compare with your work. So you have to go for a standard data set always. Otherwise, you have to test on standard data set. Then you have to consult a doctor. If in case of medical image, you have to consult doctor, get data from doctor. It should be a supervised one. Then after doing the process, you have to consult again and get unsupervised data, test on your network and give the result back to the doctor. Then the doctor will verify and tell that this is correct. Then only you can proceed further. Then you have to publish the data generally to available to other people so that the others can use the data. So your paper will get citation and also your data will be a standard one.
For research, which is better, Colab or Anaconda Navigator?
Anaconda Navigator, we can use. The thing is, if you have a GPU, then you have to use Anaconda. Otherwise, you have to go for Colab.
The next one is, how can I use DL for flat data sets?
Flat data set in the sense, what do you mean by flat data set?
Maybe they are talking about 1D data, I think.
1D data, yes, yes. 1D data set we can use. It will be one-dimensional convolution then.
So participants, are there any other questions?
Have you used the LIDC or IRDA database for lung detection? No. We are using specific data set. Just a minute, I will tell you. For the lung data set, it is available in net. It is a standard data set. I will tell you now. Lung data set which is used is lung data set is LungX challenge database. LungX challenge database. It is available in website.
The next question.
Okay.
The next question is, any plant data set available for training?
Part size involves one accuracy. Okay, see, in part size case, see, say for example, if you have a image, you can give in two ways. One, we can give the image as a whole, or you can split the image into patches and give. So patches are giving in the sense, you have two operations. One is global operation and second one is local operation. If you're giving your image as a full image, it will globally look at the feature. But if you give a patch-based image, putting it into small pieces, so each CNN will look at it in the patches. So it will get more concentration. So patch-based may be much better compared to a whole image case. So patch-based may improve the accuracy.
When they talk about plant images, are they meaning about the disease detection in the plants?
Yes.
Maybe.
First thing is yield prediction. Second thing is disease prediction. Next is crop, how much the crop is ready. These three can be done. Then counting can also be done. For that counting, that's what I told you. YOLO, V3 or SSD networks are used.
For object detection algorithm.
Yes, object detection algorithm. So there we are combining 2 or 3 algorithms together. And another option, see, you can see the existing networks, and when you use the existing networks, you may have some problem of less accuracy. Then you can redefine the structure. That is also another novelty. You can redefine the structure and you can check for the results. If it is getting better, you can say that I redefined or modified. There are some more papers. We can see that modified AlexNet, all those things are available. So we can do modification to that also.
Dr. Biju?
Any information loss in biomedical image with the BGM format? No. See, generally all the format in image are lossy format. The main content with, see, for example, DICOM images, we are taking an image in a raw image. Raw image is having large size. That's why we are compressing, because of lack of bandwidth, we are compressing the image into DICOM standards. In DICOM standard, we are having the image size is less than 2 GB. Actually, the image is not 2 GB, it is more in size. There itself a compression happens. So DICOM image is almost good. Better to use the TIFF images. TIFF is uncompressed, TIFF can be used. JPG, PNG, all are compressed one.
Are there any other questions from the participants?
Anisha, maybe we can wind up.
Yeah.
Plant situation, can we take real-time pictures? Yes. For plant disease identification, we can take real pictures, so no problem. So you can use as a data set. Once the data is published, the thing is, you are taking your own data set. You have to verify your data set with other works. If you are comparing with existing methodologies, you have to implement your work, then test on your data, then you have to compare. Then it will be fine. Then you can make it public. Image conversion is compulsory, sir, or shall we give DICOM? DICOM can be directly read, no problem, we can do.
So if are there any other questions? Okay, so if there are no other questions, I think we wind up for today. Thank you so much, Dr. Varun.
Thank you.
For being with us today. Thank you for taking time and being with us. It was a very informational and enlightening talk, sir.
Thank you.
Thank you so much.
Okay, so I would like to thank Team Karunya for inviting me to your program, especially my friend and my well-wisher, Dr. Jude Hemant. So we are very close earlier back. So I'm very thankful to you, sir, for inviting me. And also, without participants, no program will be successful. All the participants are very cooperative. Thank you, all participants. Thank you. Have a nice day.
Thank you. Thank you, Varun. We will see face to face in our university when all the COVID situation gets over.
Yes.
Thank you. Thank you very much for sparing us.
Okay. To all, stay safe. Thank you.